Look up at the night sky for a second. Imagine we zoom in on what looks like a perfectly ordinary galaxy, and you notice a glowing ring wrapped around it, like a cosmic halo. Now here's the twist. That ring isn't really there. It's the same light from the same distant galaxy, bent into a circle by gravity itself. Because here's what nobody tells you. The night sky is lying to you. Not in a small, poetic way, but in a very literal, your eyes are being rerouted by invisible mass way. You were taught to trust this simple picture. Light leaves a star, flies in a straight line through empty space, and lands cleanly in your telescope. You know the one. The classroom laser beam mental model. The straight arrow on the diagram. The idea that photons are tiny, disciplined soldiers marching across the universe. So, let's start at the very beginning. You're in school, someone shines a laser across the room, and you're told, more or less, that's what light does in space. Straight lines, flat paths, no nonsense. And that works until you zoom out, because on cosmic scales, those straight lines begin to curve. Light can be bent, split, magnified, even wrapped into perfect rings that hover around galaxies like ghostly bracelets. This is where the sky starts to cheat. A massive galaxy or a whole cluster drifts between you and something even farther away, and its gravity doesn't just pull on planets or clouds of gas. It pulls on the path that light wants to take. The result is gravitational lensing. One galaxy turning another into arcs, smears, multiple copies. Or in those rare, eerie cases, a nearly perfect circle of light called an Einstein Ring. And here's the paradox that should bother you. Light has no mass. It isn't a rock. It isn't a planet in orbit. It's not some glowing marble you can push around. So how can something that isn't touching it, across millions or billions of light years of empty space, force it into a flawless halo? What does that say about the shape of space-time between you and that distant galaxy? Is space really flat at all, or are we peering through a funhouse mirror and calling it reality? Now let's begin to really break your mental picture. Einstein sat down with pencil and paper and predicted that gravity would bend light, and that if everything lined up just right, it would draw a ring in the sky. For decades, this sounded like science fiction, more than astronomy. No telescope on Earth could actually see those delicate circles. They lived mostly in equations and imagination. But the universe turned out to be even stranger than the math made it sound. Modern observatories, from Hubble to JWST, now capture these cosmic halos in absurd detail. Glowing blue arcs around red galaxies, nearly complete rings like the cosmic horseshoe, little space donuts that are really gravity in action. Each one is a lie the sky tells your eyes, and a truth about what's hiding in the dark. Tonight, we're going to peel back that lie. We're going to learn what an Einstein ring really is, why gravity can carve a circle out of starlight, and how these warped halos let us map invisible dark matter and look deep into the past of the universe. Because once you see how the sky bends, you will never trust a straight line in space again. So here's the part that feels like a magic trick. You point a telescope at a distant galaxy, and instead of seeing a neat little smudge in one spot, you see it torn into glowing arcs. Sometimes, if the alignment is just right, you see a full circle, a ghostly ring of light wrapped around a closer galaxy, like a halo that galaxy never earned. Now let's begin with the simplest version of the paradox. That background galaxy is not actually arranged in a ring. It's not shaped like a donut. It's sitting in one place, minding its own business, billions of light years away. And yet, on our sky, it appears smeared into a curve or a perfect loop. How can one galaxy be in one place out there, but in many places at once up here? Because here's what nobody tells you. This is not a camera glitch. It's not your eyes being fooled by some optical illusion in the atmosphere. The ring is a real pattern in where the photons land on our detectors. Gravity has literally rearranged the arrival directions of light, bending the paths of those photons as they thread past a massive object on the way to you. In other words, space itself is acting like a lens. A whole galaxy, or even an entire cluster of galaxies, becomes the curved glass. The background galaxy is the light source. We are the screen. When the source, the lens, and us fall almost perfectly in line, the light is bent symmetrically around the lens, and an Einstein ring pops out on the sky. Miss that perfect alignment by a little, and the ring breaks into arcs, streaks, or multiple distorted copies. And this is not some tiny, delicate effect. Some of these rings span angles larger than the full moon. Think about that the next time you look up and see the moon hanging there. Now imagine that whole circle replaced by a warped, magnified echo of a galaxy that has spent more time traveling to your eyes than the solar system has existed. That's what our telescopes are catching. You've seen the pictures? The cosmic horseshoe, nearly a full loop of blue light around a massive red galaxy. Giant arcs wrapped around clusters like Abel 370, where invisible dark matter does most of the bending. JWST images where faint primordial galaxies are stretched into delicate curves, quietly boosted in brightness by gravity, so we can spy on the first billion years of cosmic history. And yet, something is above the planets. Something is below them. Not in the solar system this time, but on the sky itself. Hidden layers of mass we only notice when they twist the light. Those distorted halos let us map dark matter we can't see, test whether Einstein's picture of gravity still holds, and turn galaxy clusters into natural telescopes. Once you understand that, every Hubble or JWST image changes. You start hunting for arcs and rings. You start wondering, whenever you glance up at the night, how much of the universe you see is already bent. And in the next part, we're going to pull that lens apart and show you exactly how mass can sculpt a circle out of straight-line starlight. So before we start actually bending light, can we press pause on the cosmos for just a second? If you're still here, still thinking about galaxies twisted into glowing halos, you're our kind of person. You're the kind of person who doesn't just want a prettier space wallpaper. You want the underlying mechanism. You want your mental picture of the universe broken and then rebuilt in higher resolution. Because here's what nobody tells you. Once you've seen gravity literally redraw the sky, you can't go back to the old flat diagrams. So here's the ask, and we'll keep it simple. If the idea of gravity turning a distant galaxy into a ring of light makes you feel even a little bit fascinated or slightly unsettled, tap like and subscribe. That's it. One tiny click on your side, but in this strange digital universe, that click is the difference between deep dive into Einstein rings and lost under 10 reaction videos to space memes. Algorithms don't wake up in the morning and say, you know what the world needs? More general relativity. They push what's quick and familiar. We're trying to push the opposite. Slow, weird questions about space-time, dark matter, and why a galaxy cluster can behave like a natural telescope. When you interact, you're not just helping this channel. You're quietly voting for more long-form, high-resolution explanations to exist in people's feeds. So, a quick interactive challenge for you. Don't overthink it. Just go with your gut. Pause for a moment and drop a guess in the comments. How many separate objects have to line up just right to make a perfect Einstein ring in the sky? Not a messy arc, not a stretched smear, but a clean, almost circular halo. Is it 2, 3, more than that? And yet something is above the planets. Something is below them. In the same way, something has to be in front of and behind in this cosmic alignment. Lock in a number down there, because later in the video, we're going to reveal the answer and unpack exactly what each of those players is doing. We'll go from the background galaxy to the invisible mass in between, to us sitting here on our tiny world, and we'll show you why even a small misalignment shatters the ring into arcs and multiple images. All right, now let's begin properly. So, let's start at the very beginning with the simple picture of gravity and light you already carry around. You know the one. Light travels in straight lines. Gravity pulls things down. In the next section, we're going to warp that flat picture into something much stranger and show you how space-time itself can curve those straight lines into a circle. So let's actually walk into that picture you already have in your head, the one every textbook quietly agreed on. A flat white page, the sun drawn in the center like a perfect yellow coin, and the planets marching around it on neat, thin ellipses. No mess, no depth, just a clockwork solar system pressed onto paper. You know the one. Little arrows shoot out from the sun in straight lines, showing light racing away in all directions. Those arrows are razor thin, perfectly straight, and they never wobble. Light goes out, planets go around, and the whole thing looks like it could have been drawn with a compass and a ruler in a single afternoon. Because here's what nobody tells you. That diagram isn't just teaching you where the planets are. It's training your brain to believe that space itself is a flat, rigid stage. The sun is a dot on the page, the planets are dots on the page, and the invisible backdrop that holds it all is also just the page. Think back to high school physics. Lasers were always thin red lines on the board, perfectly straight. A mirror was a flat rectangle, and the light ray came in at one angle and bounced off at the same angle. No hesitation, no bending unless it hit something solid. Light was treated like tiny bullets or billiard balls, ricocheting cleanly when they met a wall. We did the same thing with gravity. We drew the Earth as a circle and sketched arrows straight down to show why apples fall. We put the sun on the page, then drew gravity as invisible arrows pointing toward it, pulling planets into their orbits like coins sliding around a table. If you spun the coin just right, it would circle gracefully. If not, it would spiral in. In that world, you can imagine marbles rolling in perfect circles on a smooth floor. Nothing curves unless it's pushed. Light doesn't bend unless it hits glass or metal. Gravity is a force that reaches across empty space like a set of invisible strings, tugging but never changing the stage itself. Does anything in that picture ever suggest that the page could wrinkle? And notice the key word we keep smuggling in. Flat. Flatboard, flat page, flat screen. The solar system orbits in a flat plane. The light rays are flat lines. Even when we say space is curved in passing, the diagram we show you is still a two-dimensional sketch pretending to be the whole story. And yet, something is above the planets. Something is below them. The real universe is not confined to that drawing. In the next part, we're going to take those straight red lines for light, that flat plane for orbits, and ask a dangerous question. What happens when gravity doesn't just pull on objects, but on the very paths those lines are allowed to take? So here's the trap. The moment we draw those straight red lines on a flat sheet, our brains quietly sign a contract with the picture. We accept that space is this smooth, empty stage, that gravity is just arrows tugging on objects, and that light is the one honest thing that never bends unless it hits glass or fog. You know the one. The classic diagram, a grid, a bowling ball sun in the middle, a little marble planet rolling around the dent. It's not exactly wrong. It captures something real about how gravity behaves. But because it lives on a flat page, it hides the most important part of the story. What space itself is doing when mass is around. Because here's what nobody tells you. When you see gravity drawn as arrows on a flat grid, you start to believe that the grid is just a convenient backdrop, like graph paper behind a physics problem. You see photons as straight chalk lines, planets as dots, and you unconsciously assume that space is a passive, unchanging background that never gets a vote in how things move. So let's start at the very beginning of how your intuition gets trained. In school, we sketch orbits as perfect ellipses on a plane. We draw the path of a laser as a ruler straight arrow, and we label the region in between as empty space. No texture, no structure, no personality, just blank white. Now imagine a different picture. You're far from the solar system, at a safe distance, with a ridiculous sci-fi laser pointer in your hand. You aim it so that the beam passes just above the visible edge of the sun and keep going toward a distant galaxy. What do you expect to see? Most people imagine a perfectly straight beam that threads past the sun and continues in a line forever, like a sniper shot through nothing at all. That expectation comes from a hidden assumption, that between you and that galaxy, there is literally nothing there except vacuum, and that emptiness can't have structure or curvature of its own. If there's no gas cloud, no mirror, no lens, then what could there possibly be for the light to interact with? The flat sheet taught you that nothing means featureless. Einstein's big move was to take that background seriously, to say, what if the grid itself can bend, stretch, and curve when mass is around? If the sun doesn't just sit in space, but reshapes the geometry of space, then the straightest possible path for light is no longer straight in the way we usually mean. It's straight inside a curved arena. And once you let the arena curve, those innocent red lines start doing something wild. They can swing around stars, split into multiple apparent paths, and in just the right alignment, wrap into a glowing circle. In the next part, we'll fire that imaginary laser past a real galaxy and watch how a simple line turns into an Einstein ring. So here's the weird part. When that laser line swings and wraps and splits, from the light's point of view, it isn't bending at all. If light could talk, it would swear it's going straight. No hesitation, no apology. Because in Einstein's picture, straight doesn't mean what you think it means. It doesn't mean looks like a ruler line on a flat picture. It means something deeper. The path that feels like no force is acting. The path of least resistance through curved space-time. Mathematicians give it a fancy name, a geodesic. You've met geodesics before, just not in space. Think about Earth. Think about an airplane flying from New York to Tokyo. You know the one. You look at a flat map and the route is this weird arc, swooping up toward the Arctic like the pilot got lost. But on a globe, that same path is the shortest way. It hugs what's called a great circle, the closest thing to a straight line on a sphere. Because here's what nobody tells you. The map is lying. The plane is not turning north and then turning back down in some dramatic zigzag. It's just cruising straight along the curved surface of Earth, following a geodesic. The only reason it looks bent is that you flattened a round world onto a flat page and then trusted the page more than the planet. Now swap Earth's surface for space-time itself. Mass and gravity don't just pull on things inside space. In Einstein's theory, they reshape the arena. They curve the very fabric that defines what straight means. So a photon leaving a distant galaxy does what it always does. It follows a geodesic, the straightest possible path in that curved geometry. No engines, no steering wheel, just free fall along space-time's version of a great circle. From our seat here, with our flat mental map of the sky, that same path can look bizarre. It can look like light is bending around a galaxy, or splitting into multiple copies of the same quasar, or even looping into a nearly perfect circle. But to the photon, nothing dramatic is happening. No sideways shove, no sudden turn, just straight motion in a curved arena. And yet something is above the planets. Something is below them. Not because space secretly has an up and down, but because every massive object redraws the local meaning of straight, the way a globe laughs at your flat map. So once we accept this new meaning of straight, gravity making a ring of light stops being magic and starts being geometry. A very strange kind of geometry. In the next part, we'll finally let that straight beam pass a real galaxy and watch how, step by step, a single line becomes a halo. The surprising part? The ring isn't where the light goes wrong. It's where our picture does. So if the ring is where our picture goes wrong, but tonight's mission is simple. We're going to fix the picture. When you see one of those viral space donuts from Hubble or Joe WST, what are you actually looking at? Is that a real circle of stars out there in space? Or a single galaxy smeared into a halo by gravity? And if those photons left some distant galaxy in straight lines, what crazy path did they follow to arrive as a perfect ring around another galaxy in our sky? Because here's what nobody tells you. Every Einstein Ring photo is secretly a map, not just of where the background galaxy is, but of the invisible mass in between. By the end of this video, when you see a blue arc wrapped around a golden galaxy, you won't just think, pretty. You'll think, I can read the gravity that did that. Now let's begin by laying out our flight plan. First, we're going to build a clean mental model of curved space-time and gravitational lensing. Not the full tensor calculus version, but a version you can actually carry around in your head. We'll start with intuitive analogies, rubber sheets, glass lenses, that sort of picture, and then carefully upgrade them so they don't lie to you. Second, we'll zoom in on alignment. What has to line up? Source, lens, and us, so that a distant galaxy doesn't just look a little stretched, but turns into a ring. We'll meet ideas like the lens equation and the Einstein radius. But in plain language, how heavy the lens is, how far everything is, and what angle on the sky that ring will have. Third, we'll flip the problem around and use the ring as a tool. Astronomers take systems like the cosmic horseshoe, or those wild arcs and clusters like Abel 370, and work backwards. From the shape of the light, they reconstruct where the mass must be. Even the dark matter we can't see at all. A ring becomes a weighing scale. An arc becomes a contour line on a gravity map. So, let's start at the very beginning of that transformation in your head. Right now, you might feel gravity as a simple pull, the thing that keeps your feet on the floor and the planets in orbit. By the time we're done, you'll see it as a sculptor of light, quietly reshaping entire galaxies into circles and crescents. And yet, something is above the planets. Something is below them, Those new JWST halos lighting up your feed are telling us about dark matter, galaxy evolution, even the expansion of the universe, and most people scrolling past have no idea. Stay with us through the analogies and into the equations without the math, and you'll walk away able to look at the next Einstein Ring image and say, I know what path that light took and what invisible cloud of gravity it passed through on the way. So to really see how gravity can sculpt a ring of light in empty space, we have to rewind. Not to the first Einstein ring, but to the first falling apple. You know the one. Newton watches an apple drop, looks up at the moon, and has the outrageous thought that both are falling for the same reason. He writes down a simple rule. Every mass pulls on every other mass with a force that gets weaker with distance, following an inverse square law. That single idea ties together apples, cannonballs, planets, comets. For centuries, it works absurdly well. You can predict eclipses, aim spacecraft, map the solar system like clockwork. On paper, the universe becomes one giant, well-behaved orbit. Because here's what nobody tells you when you see that neat textbook picture. Even Newton's clockwork had a little wobble in it. Mercury refused to play along. Its orbit doesn't close perfectly. The point of closest approach to the sun slowly precesses. Astronomers measured that precession, subtracted every known effect, and still there was a tiny leftover. Not huge, just enough to whisper that the law of gravity was almost right, but not quite. So what did we do? We added a fudge factor. Maybe there was an unseen planet, Vulcan, tugging on Mercury inside the orbit of the solar system we knew. For decades, people hunted this phantom world. No planet, no asteroid belt, nothing. The math was screaming that the force picture was missing something more fundamental, and we were trying to patch it with invisible rocks. Enter Einstein. He does something outrageous. He takes gravity out of the force category entirely. Instead of masses pulling on each other through space, mass and energy reshape the stage itself. They tell space-time how to curve, and that curved space-time tells matter how to move. Planets aren't being yanked by an invisible hand. They're following the straightest possible paths in a geometry that isn't flat. To visualize it, we drag out the famous trampoline. Put a bowling ball in the middle of a stretched sheet. Drop a marble, and you see it spiral in or settle into an orbit. It's a useful picture. You can feel how a dip guides motion. But notice the cheat. In that analogy, the marble is pulled down by Earth's gravity to reveal how gravity works. Real space-time is four-dimensional, with 3 dimensions of space plus time all warping together, and there's no extra down direction for it to sag into. Now let's begin to connect this to light, because in Einstein's picture, anything with energy follows those curved paths, not just things with mass. Light has no rest mass, but it absolutely carries energy and momentum. So when a beam of starlight passes near a massive galaxy or cluster, its path bends, just like Mercury's orbit bends, just like a marble on that sheet curves around the bowling ball, which means an apple doesn't just fall. Starlight falls too, and once you accept that, the idea of a perfect halo of light around a hidden mass stops being magic and starts being geometry. So if starlight can fall, the obvious question is, has anyone ever actually seen it fall? Not in a simulation, not in a thought experiment, in the real sky. To answer that, we have to rewind to one of the most dramatic experiments in the history of physics. Now let's begin on a tropical island, under a darkening sky, in 1919. The moon is about to slide perfectly in front of the sun. Total solar eclipse. The one chance astronomers have to stare right next to the sun without being blinded. Here's the trick they tried to pull off. They photographed a patch of stars when the sun was nowhere near it in the sky. Then, during the eclipse, they pointed their telescopes at that same patch, now hidden behind the black disk of the moon, with the sun lurking just behind. If gravity bends light, those background stars should appear in slightly different places. If not, the universe goes back to Newton's picture, because here's what nobody tells you. Newtonian gravity did predict a bend, a tiny deflection of starlight as it skimmed past the sun. But when Einstein ran the numbers with space-time curvature, he got almost exactly twice that angle. Not a philosophical difference, a measurable one, a bet you could settle with glass plates and a ruler. So the expeditions went out. Arthur Eddington and colleagues, ships loaded with telescopes and fragile photographic equipment, all depending on a few minutes of clear sky. Clouds threatened, the atmosphere shimmered, the timing was brutal. You can almost feel the tension. If the images came out blurry, the whole test would evaporate. But they got their plates. They took them home. They compared the positions of those stars with their positions when the sun wasn't there. And what did they see? The apparent star positions were shifted outward, away from the sun, by almost exactly the amount Einstein had predicted, within the messy experimental error of the day. Nothing in those distant star systems had actually moved. Their orbits out there in the galaxy were untouched. What changed was the path their light took through the curved space-time around our sun. As those photons skimmed past, gravity nudged them. So the stars drew a slightly different picture on our sky. It's a tiny effect. Less than 2 arc-seconds for light grazing the sun's limb. But that almost invisible wiggle is the same basic lensing that, on much larger scales, lets entire galaxies and clusters twist background galaxies into smeared arcs, mirrored doubles, and full Einstein rings. And yet, something is above the planets. Something is below them. It's this invisible scaffolding of warped paths that light can follow. Because once you see that in a simple eclipse, you have to ask, what happens when the lens isn't just a star, but a whole cluster of galaxies, and the alignment is almost perfect? What happens is that gravitational lensing splits into 3 very different regimes. 3 ways that gravity can redraw the same background our universe, depending on how much mass you have, how it's arranged, and how perfectly everything lines up. So let's start at the very beginning. Weak lensing. This is gravity in whisper mode. Individual galaxies in a deep Hubble or JWST field look almost normal to you. A little stretched, a little skewed, nothing dramatic. But when you take millions of them and stack their orientations statistically over a huge patch of sky, a hidden pattern pops out. You see that, on average, their shapes have been sheared in one direction by the combined pull of foreground clusters and the vast cosmic web. Because here's what nobody tells you. Weak lensing is less about pretty pictures and more about cartography. It lets us draw maps of invisible, dark matter on scales far bigger than our solar system, tracing filaments of mass that would otherwise be completely dark. You don't get a single spectacular ring. You get a quiet, global signal that only appears when you average like a cosmologist instead of staring like a tourist. Now turn the dial up. Strong lensing is when gravity stops whispering and starts shouting. Here the mass is concentrated in something intense, like a massive galaxy or a cluster such as Abell 370, and the alignment with a background galaxy is good. Really good. Light paths that would have missed us are bent back toward our line of sight. One distant galaxy can appear as multiple images, mirrored across the lens, or stretched into giant arcs that wrap part way around it. Push the alignment closer to perfect, and the geometry does something outrageous. The background galaxy's light is deflected into a nearly complete circle, an Einstein Ring. You know the one. Those glowing blue halos around a reddish central galaxy in Hubble posters, or the space donuts JWST keeps dropping into your feed. That's not a ring in space. That's one galaxy seen in every direction around a lens because space-time itself has been curved that much. Then there's the opposite extreme, microlensing. Here the lens isn't a galaxy cluster, it's a single star, a brown dwarf, even a planet drifting through the Milky Way. The gravity is tiny compared to a cluster, but if that object passes almost exactly in front of a background star, its field focuses the starlight just enough to make the star brighten for days or weeks. No arcs, no visible stretching, just a smooth rise and fall in brightness that tells you a compact object crossed the line of sight. And yet something is above the planets. Something is below them. In microlensing, that something can be a hidden exoplanet, tugging on the light curve, revealing itself without ever emitting a photon we can see. So now we have our three regimes: weak, strong, and micro. Each one is a different kind of detector. Weak lensing lets us weigh the cosmic web. Strong lensing and Einstein rings let us map dark matter in individual galaxies and clusters with absurd precision. Microlensing lets us count rogue planets and dark wanderers our telescopes can't resolve. Because once you realize that, you start to see gravitational lensing not as one effect, but as a whole toolkit. And in the next section, we're going to pick up that toolkit and ask a very specific question. What can a single, nearly perfect Einstein ring tell us about the invisible mass holding it in place? So if an Einstein ring is part of this lensing toolkit, we should talk about the word that sneaks into every explanation: lens. Because here's what nobody tells you. That word is both perfect and completely wrong. You've used a lens your whole life, a magnifying glass, a camera lens, a pair of glasses. You know the one, a curved piece of glass that bends light rays, pulls them together, and makes small print look bigger and brighter. Move it over a page and suddenly the letters swell, the edges sharpen, the world under that circle looks enhanced, almost important. Now let's begin to scale that picture up. Take a massive galaxy or a whole cluster like Abell 370 and imagine it acting like a cosmic magnifying glass. Light from a faint galaxy far behind it passes near all that mass, gets bent, and reaches us from slightly different directions. To your eye, or to Hubble or JWST, that distant galaxy can look stretched, brighter, even split into multiple images. In the rare, almost perfect alignment, it becomes a ring, a glowing, gravitational magnifying glass in space. So far, the analogy feels great. A lens in your hand, a lens in the cosmos. But here's the problem. When you look at a real magnifying glass, there's a clear surface. There are edges. You can tap it, smudge it, chip it if you're unlucky. You can see exactly where the glass ends and the air begins, where the bending of light is happening. A gravitational lens has none of that. There is no shimmering boundary in space where light suddenly hits the lens. There's no cosmic contact lens floating between you and a distant galaxy. It's just mass. A cluster of galaxies here, a dark matter halo there, an invisible cloud of gravity spread out with no obvious edge at all. So, let's start at the very beginning of what's really going on. In glass, light bends because it slows down as it crosses from air into a denser medium. In gravitational lensing, there is no medium. There's only curved space-time itself, telling light what counts as a straight line. Photons follow the straightest possible paths in that curved geometry, and to us those paths look bent, and yet something is above the planets. Something is below them. In the same way, something is inside the lens and outside it, even though there's no physical shell. That something is just regions of space-time where the curvature is strong enough to redirect light toward us, which raises a sharper question. If there's no glass surface to trace with your finger, what actually sets the size and shape of an Einstein ring? How can we go from a messy, extended cloud of mass to a precise circle on the sky using only gravity and distance? Hold that thought, because in the next section we're going to turn that question into an actual calculation, and the answer will tell you how to weigh the invisible. So if there's no glass sheet in space, what is doing the tracing for us? What actually tells a light ray, turn here, not there? To see that, we have to talk about mass as a sculptor. Because here's what nobody tells you. Gravity isn't really a force yanking on light. It's mass reshaping the stage that light moves through. Picture space-time not as a flat page, but as a flexible, invisible landscape. Drop in a galaxy, and you don't just get a little dent. You get a deep, smooth basin. The more mass you pour into that region, the deeper and steeper that basin becomes. A light ray is like a marble rolling across that landscape. It wants to move straight, but if the terrain tilts under it, the path curves. Pass near a massive galaxy cluster, and the slope is so strong that light from background galaxies can be swung far off its original course. Now let's begin to add some order to that picture. For a roughly spherical mass, say an isolated galaxy, or a dark matter halo, the basin it carves is almost perfectly symmetric. From above, the contours are like concentric circles around the center. That symmetry means something powerful. If two light rays skim past on opposite sides at the same distance from the center, they feel almost the same tilt in space-time and get bent by nearly the same angle. Different directions, same radius, same deflection. That radius has a name in lensing language. It's related to what physicists call the impact parameter, how close the light's path comes to the center of mass as it flies by. Big impact parameter, you're cruising along the gentle outer slopes, barely nudged. Small impact parameter, you're diving close to the core of the well, and space-time is tilted so sharply that your path swings much more dramatically. Same galaxy, same mass, completely different bending, just because you passed a little closer. So, let's start at the very beginning of a ring. Imagine a background galaxy sending out light in all directions. Some rays miss the lens entirely. Some pass very far away and are barely deflected. But there's a special band of impact parameters where the bending is just right. The light is redirected straight toward us. Because of that near-perfect symmetry, all those just right paths lie at essentially the same distance from the center of the lens. On our sky, that distance turns into a circle. You know the one, the Einstein Ring. That circular angle is called the Einstein radius. And here's the part that should make you sit up a little. There's a remarkably simple formula that links that radius to 3 ingredients. The mass of the lens, the distance from us to the lens, and the distance from the lens to the source. Change any of those, and the ring grows or shrinks. In the next section, we're going to unpack that relation without drowning in symbols, and you'll see how a glowing halo of light can turn into a cosmic scale for weighing the invisible. So we've got this clean little formula for the radius of an Einstein ring. But a formula on a slide is not what your brain actually sees through a telescope. Your brain sees a scene. 3 actors. 1 stage. Because here's what nobody tells you. Gravitational lensing is not just about mass and distance. It's about where you are in the audience. So, let's start at the very beginning. Actor number 1 is the source. Way out in deep space, there's a background lighthouse of light, often a galaxy or a quasar, throwing photons in every direction, all the time. It doesn't care about us, it just shines. Actor number 2 is the lens, usually a closer galaxy or a whole cluster sitting between us and that distant beacon, its gravity quietly curving space-time. Actor number 3 is you and me, the observers, parked on Earth or riding in orbit, pointing mirrors and detectors at the sky. Now picture the geometry. Light leaves the source in a giant expanding sphere, like an invisible, ever-growing bubble. Most of those photons will never meet the lens. They head off into other parts of the universe, never to enter our solar system, never to cross our little plane of orbits. But some rays pass near the foreground mass, fall into its curved space-time, and their paths bend. A few of those bent trajectories just happen to intersect the tiny target that is our telescope. Those are the ones we actually see. You know the one. The flat diagram where a straight line from source to lens to observer gives you a simple deflection angle. It's useful, but it hides the real drama. Because in 3 dimensions, there isn't one special bent path. There's a whole cone of them that can be redirected toward us from different directions around the lens. To feel it, imagine you're standing in a dark theater. Behind the stage, there's a bright spotlight shining straight toward the audience. Between you and that light, suspended in midair, is a translucent glass sculpture. As the light hits it, you don't just get a single shadow. You get smeared shapes, arcs of brightness, a distorted halo painted on the haze in front of you. That sculpture is the lens. The spotlight is the source. You, in the audience, are the observer. And just like in that theater, alignment is everything. Most of the time, the source sits off to one side of the lens from our point of view, so the bent paths don't form a perfect circle. We see stretched arcs, partial rings, or even multiple separate images of the same galaxy. That's why Hubble and JWST keep finding cosmic horseshoes and weird mirrored pairs instead of neat glowing donuts. But what happens in the rare case when the spotlight, the sculpture, and your seat line up almost perfectly, and the mass of that lens is smooth enough to act like a gentle, symmetric piece of glass? How does that 3-actor arrangement suddenly turn into a complete halo of light wrapped around the lens? And what does that ring secretly reveal about the invisible matter inside? That's where we're going next. This is what happens when the universe lines up just right. Not in some mystical way. In a very literal, geometric way. The background galaxy, the massive lensing galaxy, and you, sitting here on Earth, all fall almost perfectly along a single line in space. When that happens, gravity doesn't just make a few arcs or duplicate images. It can draw a complete circle of light. That circle is what we call an Einstein ring. You know the one. Those eerie glowing halos around a central galaxy and Hubble or JWST images, like the cosmic horseshoe that looks uncannily like a space donut. It's not a special kind of galaxy. It's the image we see when light from a distant source reaches us from all directions around the lens with the same apparent angle. From our point of view, every bent path lines up on a ring. Because here's what nobody tells you. Perfect alignment is never actually perfect. The universe is messy. The source is slightly off to one side. The lensing galaxy isn't a mathematically flawless sphere, and we are not nailed exactly to the line. But if the source is compact enough, and the mass of the lens is fairly symmetric, those imperfections don't ruin the effect. They just turn a mathematically perfect circle into an almost perfect one. So what are the photons actually doing? Picture a distant quasar firing light in all directions, like a lighthouse in the dark. Some photons leave on a path that will skim the left side of the foreground galaxy. Some skim the right, some go above, some below. As they pass through the curved space-time around that lens, their trajectories are deflected inward. They bend just enough that, far downstream, they all converge toward us and arrive with the same apparent separation from the lens on the sky. To your eye, or your telescope's detector, that looks like a ring wrapped around the lens position. Here's the subtle part. The radius of that ring on the sky is not random. It's the Einstein radius, and it's set by 3 ingredients: how massive the lens is, how far away the lens is, and how far beyond it the source sits. More mass, or a more favorable distance arrangement, means light has to bend more strongly to reach you, so the ring appears larger. Less mass or awkward distances, and the ring shrinks down. And yet, something is above the planets. Something is below them. That's how we talk when we imagine a flat solar system, and our brains try to do the same thing here. We want to believe the source itself has turned into a glowing loop in space. It hasn't. The galaxy or quasar is still a more or less normal object, sitting at one point in its own cosmic neighborhood. The ring is a projection effect, a trick of curved space-time between us and it. So the next time you see an Einstein ring, don't picture a literal hoop of stars. Picture a single distant beacon and a foreground mass quietly warping every possible path that beacon's light can take to reach you. In the next part, we'll use that warped light to do something bold, weigh invisible matter we can't see at all. So if an Einstein ring is just one galaxy copied all the way around, the next question is brutal and simple. How big is that circle in the sky? Now let's begin with a tiny unit that secretly rules this whole picture. Astronomers don't usually talk about the ring's size in kilometers. They talk about its angular size, its apparent radius on the sky. It's called the Einstein radius, and it's measured in arcseconds. 1 arcsecond is 1/3000 of a degree. You know the one. The width of a human hair held at arm's length is about an arcsecond. We're dealing with halos of gravity that small, because here's what nobody tells you. That delicate little angle is encoding the full weight of a galaxy. The Einstein radius grows with the square root of the lens mass. Double the mass, and the ring doesn't double in size. It only gets about 40% bigger. Crank the mass up by a factor of 100, and the ring becomes 10 times larger. Gravity is generous, but it's not reckless. But mass isn't the only player here. The distances matter just as much. The distance from you to the lens, from the lens to the background source, and from you to the source. Change that triangle, and you change the ring. Put the lens halfway between you and the source, and the geometry is perfect for a big halo. Slide the lens too close to you or too close to the source, and the same mass carves out a smaller angle on the sky. It's like moving a magnifying glass closer or farther from the page. The circle of light swells and shrinks. So, Let's start at the very beginning of scale. A single massive galaxy acting as a lens will often give you an Einstein ring of about 1 arcsecond. That's roughly the apparent size of Jupiter's disk in the night sky. A cosmic donut as big as a planet's face, drawn entirely in warped starlight. Now jump up to a galaxy cluster, tens or hundreds of galaxies buried in a shared cloud of dark matter. Those can throw rings tens of arcseconds across. Some of the arcs you see in Hubble cluster images are larger than Jupiter's apparent size, stretched almost cartoonishly around the cluster's core. The city lens analogy helps. Imagine walking through a city where every intersection has a different glass lens embedded in the pavement. A small light lens bends light just a little, focusing it into a tight, tiny halo. A huge, thick, heavy lens bends light strongly, pushing the bright ring out to a larger radius. The mass of the lens is like the thickness of the glass. The layout of the streets and buildings is like the distances between you, the lens, and the source. Change either, and the glowing circle on the ground changes. And yet something is above the planets. Something is below them. In lensing, that above or below is literally how far from the center the ring appears. Measure that Einstein radius precisely. Combine it with the distances from redshifts, and you can run the equation backward. You weigh not just the stars and gas, but the invisible dark matter holding the whole lens together. In the next section, we'll take that idea and push it further, turning distorted light into a full-scale map of unseen gravity. So if an Einstein ring can weigh a galaxy, why don't we see perfect glowing circles all over the sky? If gravity can make halos of light, where are all the halos? Because here's what nobody tells you. A full, clean ring is the exception. In the three-dimensional universe, perfect alignment is like threading a needle from across a city. The source, the lens, and you have to line up almost exactly along one line of sight. Shift the background galaxy a tiny bit above or below that line in space, or nudge the lens slightly off-center, and the circle shatters. The light is still bent. The gravity is still doing its thing. But the picture you get is very different. Most strong lenses don't look like cosmic donuts at all. They look like someone grabbed a galaxy and smeared it around the lens. You get long, stretched arcs curving around a massive cluster, like an Abel 370. You get mirrored pairs of galaxies on opposite sides of a foreground mass. You get quadruple images, the famous Einstein crosses, where one galaxy appears 4 times around a central lensing galaxy. Sometimes you get a partial ring, a bright arc that hints at a circle your brain wants to complete, even though only a fraction is actually there. Now let's begin to complicate the picture even more. Those textbook diagrams silently assume the lens is a perfect sphere. Real galaxies and clusters? Not so polite. They're elliptical, lopsided, full of clumps of dark matter and satellite galaxies. That messy mass distribution breaks the symmetry you'd need for a thin, uniform ring. One side of the lens might tug the light harder. Another side might barely bend it, so the would-be circle gets squashed, thickened, and torn into arcs and multiple images. And the background source isn't a perfect point either. A real galaxy has size, spiral arms, bright knots of star formation, a bulging core. Different parts of it sit at slightly different positions behind the lens, so each region follows a slightly different bent path through space-time. Instead of all the light lining up into one razor-thin ring, you get a smeared ribbon, some parts magnified into giant arcs. Other parts split into separate images, all orbiting the lens in your field of view like a distorted miniature solar system. So, let's start at the very beginning of why this mess is a gift. Those imperfections are not a bug, they're the data. By asking, what unlensed galaxy shape would produce exactly these arcs, these mirrored pairs, this almost ring? Astronomers can reverse engineer the detailed mass map of the lens. Even the invisible parts, tiny kinks in an arc, can betray a hidden clump of dark matter with no stars at all. A slight brightness change along a partial ring can reveal a subhalo the telescope can't see directly. And yet, something is above the planets. Something is below them. In lensing, there's an invisible landscape above and below those arcs too, written only in warped light. In the next section, we're going to walk through that landscape and show you how to turn a messy smear of images into a precise, three-dimensional map of unseen gravity. So let's drop into one of these warped landscapes and actually look at it. Not as a diagram, as a photograph, because here's what nobody tells you. Some of the cleanest Einstein rings we've ever seen look less like equations and more like cosmic street art. Take the cosmic horseshoe. You know the one. Catalog name SDSS JWilla 48 plus 1 1930, but your brain will remember it as a nearly perfect blue arc wrapped almost all the way around a single fat red galaxy. On the image, it really does look like someone tried to draw a full ring, missed by a few degrees, and left a glowing horseshoe hanging in space. What are you actually seeing there? The red blob in the center is the lensing galaxy, a massive system sitting in the foreground, full of older, cooler stars that give it that warm, reddish tone. The bright blue arc is not part of that galaxy at all. It's a separate, more distant, star-forming galaxy whose light has been stretched, split, and wrapped around by the gravity of the red one, pulled into that horseshoe shape along the curved path of deformed space-time. This is the same idea as the simple ring diagram we talked about earlier, but now you're staring at the real thing. Imperfect alignment turns a pure circle into an arc. Tiny clumps of dark matter in the lens twist and kink that arc. Every little wiggle is the orbit of photons being bent by an invisible mass we can only infer. And the horseshoe is not alone. If you zoom out to galaxy clusters like Abel 370, the picture gets wild. The central cluster is a swarm of yellow-orange galaxies, but all around them you see long, ghostly blue streaks and partial rings. Those are giant lensed arcs, background galaxies smeared into curves by the combined gravity of the entire cluster, tracing out the hidden dark matter halo like neon outlines on a transparent sculpture. Then there's the molten ring, Gal Plus 0.228. Hubble first showed it off, and JWST has been sharpening the view. It really does look like someone poured glowing orange glass around a central galaxy. Again, the warm reddish lens galaxy sits in front. The cooler, bluer, and sometimes more chaotic lensed features belong to much more distant, vigorously star-forming galaxies. That color contrast is a quiet clue. Older, closer galaxies tend to have more red stars and more dust. Younger, farther ones pump out hot blue light. So when you see a reddish lens with a bluish halo or arc, you're not just looking at a pretty picture. You're looking through time, across distance, and along a warped plane of gravity, all at once. Now let's begin to ask the uncomfortable question. Beyond the beauty, what is all this actually telling us? The exact thickness of an arc, the brightness along a ring, the way one side is magnified more than the other. Those are not artistic choices. They're encrypted messages from the mass distribution in the lens. In the next section, We're going to treat these space donuts like data and show you how to decode those rings into a three-dimensional map of invisible gravity. So now we actually try to read the ring, not as a pretty picture, but as an equation written in light. Because here's what nobody tells you. Every Einstein ring is an answer. Our job is to work backwards and figure out what the question was. This is the inverse problem. We don't start with gravity and predict what you'll see. We start with what you see and reverse engineer the gravity. Astronomers take the observed arcs and rings, make a guess for what the background galaxy or quasar looks like, and then build a model for the lensing mass that sits in front. Then they let the equations of general relativity bend the light in a computer and ask a simple question. Does the simulated ring look like the one in the telescope? Most of the time, the answer is no, at least at first. So they tweak the mass model, move some mass in, move some mass out, change how concentrated it is, add a small clump here, a smooth halo there, run the light through again. Does the arc get thicker on the right side, like in the real image? Does that tiny counter image appear near the center, just where Hubble or JWST spotted it? This back and forth can run thousands of times until the fake ring and the real ring are nearly indistinguishable. But what exactly are they moving around? Not just the visible galaxy. The stars, gas and dust in the lens do contribute to the bending, and we can often estimate their mass from the light they emit. Yet something else dominates. An extended dark halo, far larger than the bright core, provides most of the lensing power. You know the one. The invisible cloud of dark matter that doesn't glow, doesn't reflect, but absolutely drags light around through gravity. When the model finally matches the image, you get more than bragging rights. You get a mass map, a two-dimensional picture of how much total mass lies in each patch of the lens's projected plane on the sky. Bright knots in the arcs often demand extra dark matter clumps. Smooth stretches point to smoother halos. In a galaxy cluster like Abel 370, those giant arcs essentially trace out where invisible mass must be hiding, far beyond what the luminous galaxies alone could provide. Sometimes the universe is extra generous and gives you multiple images of a flickering background quasar. Each image sits in a slightly different gravitational potential will, so the light paths differ in length and in how much time dilation they experience. One image brightens tonight, another echoes that flicker days or weeks later. Those time delays encode the depth of the gravity wells, adding a kind of fourth dimension to the mass map. And then there are the really clean Einstein rings, perfect or nearly perfect circles. For those, the geometry is so tight that the radius of the ring nails down the total mass inside that circle. It's a cosmic weighing scale. All the stars, all the gas, all the dark matter within the Einstein radius get summed into one precise number. So, let's start at the very beginning of that number in the next section. How these gravity-built scales let us weigh the universe itself. That one precise number is where gravity leaves fingerprints on the invisible. Because here's what nobody tells you. When we read an Einstein ring, we're not just admiring a pretty halo of light. We're doing forensics on mass we can't otherwise see. So, let's start at the very beginning of that invisibility. Dark matter is our name for the bulk of the universe's matter that doesn't glow, doesn't shine, doesn't absorb or emit light at all. It just sits there in space, shaping orbits and motions through gravity. We infer it from how galaxies spin too fast at their edges, how clusters of galaxies hold together, how the whole cosmic web hangs in a gigantic, three-dimensional structure. Now here's the elegant part. Lensing doesn't care what's doing the pulling. photons don't stop to ask whether they're being bent by bright stars, cold gas, or a huge, ghostly dark matter cloud. They only respond to the total curvature of space-time. To light, mass is mass. Period. That's why gravitational lensing is such a brutally honest probe. It's agnostic to what the mass is made of. You can see this most dramatically in giant galaxy clusters like Abell 370. You look at the image and you see those big yellowish galaxies. Sure, but then your eye catches the weird blue arcs and stretched smears in the background. Those aren't sci-fi glitches. They're distant galaxies whose light has been dragged into arcs by the cluster's gravity. When you try to model that lensing pattern using only the visible galaxies, the picture falls apart. The arcs are too long, the distortions too strong, the geometry all wrong. So you add in a much larger, more diffuse dark matter halo enveloping the whole cluster. Suddenly, the predicted arcs line up with the observed ones. The apparent chaos snaps into focus. And yet, something is above the planets. Something is below them. In the same way, something invisible sits above and below those bright cluster galaxies in the mass map, thickening the cluster far beyond what your eyes can see. This is where Einstein rings become precision tools. If you can measure the radius of a nearly perfect ring around a galaxy or a cluster, you get a robust estimate of all the mass enclosed inside that circle. Over and over, that enclosed mass turns out to be far greater than what the stars and gas can account for. The ring is basically shouting, there is more here than meets the eye. But if lensing is so sensitive to mass, what happens if the rings and arcs ever refuse to match our best dark matter models? Could the halo's fingerprints hint at modified gravity? Or some new ingredient in the cosmic recipe we haven't even named yet? Hold that question, because the next step is to see how these warped pictures let us test not just dark matter, but gravity itself. So if warped rings can weigh invisible halos, what else can they do? Here's the twist. They don't just map space. They let you peek across time. Now let's begin with a quiet but brutal fact about the universe. When you look out, you never see things as they are. You see them as they were. Because light has a speed limit, a galaxy a billion light years away is a billion-year-old message. You're not looking across distance, you're looking down a timeline. Because here's what nobody tells you when you first see those gorgeous Hubble and JWST deep field images. Every faint smudge is already a time machine. The farther out you go, the younger the universe you're sampling. At a few billion light years, galaxies are still assembling. At 10, they're toddlers. Push to 13 and you're skimming of the cosmic baby photos when stars were just learning how to ignite in huge clouds of gas. But the universe didn't make this easy for us. Those early galaxies are tiny, dim and buried behind oceans of intervening space. Our telescopes, even the best ones in Earth orbit, hit a wall. So nature cheats for us. Massive galaxy clusters bend space-time so violently that they turn into gigantic natural telescopes. Their gravity pulls passing light rays inward, magnifying and brightening whatever sits behind them. This is strong lensing. You know the one. The dramatic arcs and stretched smears wrapped around a fat cluster core. In the perfect alignment, the background galaxy isn't just doubled or smeared. It's wrapped into an almost complete circle, an Einstein ring. It looks like a decorative halo, but hidden in that circle is a brutally magnified view of a much more distant, much younger galaxy. Here's the pattern interrupt. That pretty ring you see on a JWST poster. It might not be some nearby showpiece. It might be a galaxy from when the universe was less than 1 billion years old, stretched into a loop but still carrying razor-sharp clues about its structure, how its stars are forming, how dust and gas are swirling in its disk. Astronomers can mathematically unscramble the ring, reverse the lensing, and reconstruct what the original galaxy looks like. This is where JWST changes the game. Its infrared eyes see light that started out in the ultraviolet, from scorching young stars, but has been stretched by cosmic expansion. Combine that with gravitational lensing, and suddenly we're spotting galaxies so massive, so early, that they're putting pressure on our models of how fast structures could assemble after the Big Bang. Did stars form more efficiently? Is our picture of dark matter's role incomplete? And yet, something is above the planets. Something is below them. In a sense, the sky you see is layered in time, not height. So if gravity can bend light into a ring and also act as a time machine, how much of what you're seeing up there is a faithful snapshot, and how much is a distorted, delayed echo of a universe that no longer exists? So if the sky is already a time-layered illusion, what happens when we zoom all the way in? What if that dramatic halo of light from a galaxy cluster has a tiny, almost ghost-like cousin hiding inside a single pixel? Because here's what nobody tells you. The same gravity that can stretch a distant galaxy into a giant ring can also turn an ordinary star into a lens. Not a poetic metaphor, a literal, physical lens in space. When a single star, even a wandering planet, drifts in front of a more distant background star, the geometry is exactly the same as an Einstein ring. Source, lens, observer, all lined up along a nearly straight line. So, let's start at the very beginning of this small-scale version. You have a background star. Between you and that star, some other object is quietly orbiting the galaxy. A dim star, a brown dwarf, a rogue planet, maybe even a lonely black hole. Its gravity curves space-time, and the light from the background star takes multiple bent paths around it. In principle, you get several images of that star, or even a perfect little ring. There's just one problem. The ring is microscopic on the sky. The angular separation of those images is measured in microarc seconds. You know the one. An angle so tiny that if you tried to resolve it, you'd need a telescope the size of the Earth's orbit. Our best telescopes, they see one blended dot, no visible ring, no split images. So what do we actually see? A flicker, a temporary brightening of the background star as the lens crosses our line of sight. The light curves around the lens from all sides, so from our perspective the star doesn't move or split. It simply swells in brightness along a very particular pattern, then fades back to normal. That rise and fall in the light curve isn't random noise. It encodes the mass of the lens, how fast it's moving, even whether it has planets tagging along. Now let's begin to appreciate how wild this is. Without seeing a ring at all, we can still say, there was a star of such and such mass that passed in front, and oh, by the way, it had a planet about this heavy at this orbit. Microlensing surveys have used that trick to find exoplanets thousands of light years away, brown dwarfs that barely glow, and compact objects like isolated black holes that give off no light of their own. And yet something is above the planets. Something is below them. On the biggest scales, galaxy clusters carve enormous halos of light into the sky. On the tiniest scales, a single rogue planet can, for a moment, make a perfect Einstein ring that you'll never see. Different masses, different distances, same underlying picture. If gravity bends light and the alignment is just right, space draws a circle. So if even invisible planets can betray themselves this way, what else is out there, warping light in silence, waiting for us to notice its shadow in a star's brief, stolen brightness? To catch those shadows in the light, we need one more ingredient: a rule. A simple relationship that quietly decides where those warped images will actually appear in the sky. This is where the lens equation walks in. Don't panic at the word equation, because here's what nobody tells you. Underneath the scary symbols, it's just geometry plus gravity, telling you how far the universe is cheating with your line of sight. So, let's start at the very beginning. Picture a straight line from you to the lensing mass, like a galaxy or a lonely planet. That line defines your zero direction on the sky. Now imagine the real source, the background star or galaxy, sitting slightly off that line. If there were no gravity-bending light, you'd see it at some small angle away from center. Call that the true source angle. But gravity doesn't let the light take the straight path. The light swings around the lens, its path bent, and it reaches your telescope from a slightly different direction. On your sky, you measure a different angle, the image angle. You know the one. It's where the mirage actually appears. Draw it as a side view. Observer on the left, lens in the middle, source on the right. A straight line from you to the lens, then a bent path from the lens to the source. We label 3 angles along that line of sight: the true source angle, the apparent image angle, and the deflection angle, the tiny kink caused by the lens's gravity. Qualitatively, the lens equation just says image angle equals source angle plus a deflection term. That's it. One angle equals another angle plus how much the light got kicked. The kick depends on 2 things: how massive the lens is and how the distances between you, the lens, and the source are stacked in space. Change the mass, you change the deflection. Change the distances, you change how that deflection projects onto your sky. The math version packs this into a tidy formula. But the idea is simple. Gravity shifts the apparent position of the source by an amount set by mass and geometry. Now here's the fun twist. That same lens equation can have more than one solution for the image angle. In other words, there can be several directions on the sky where bent light from the same source can arrive at you. Solve the equation. Get multiple answers. See multiple images scattered around the lens like a broken halo. And when the source sits almost perfectly behind the lens, something dramatic happens. Symmetry kicks in. Every direction at the same angle from the center becomes a valid solution. The possible image positions don't just come in 2s or 4s. They wrap all the way around into a full circle. That special angle is the Einstein radius. And the glowing ring you see is just the lens equation, made visible. But what if that circle isn't perfect? What if the mass isn't smooth, or the alignment is just a little off? That's where the real detective work begins. So when that circle breaks, it doesn't just smear into a random mess. Sometimes it snaps into one of the strangest optical illusions in the universe. One galaxy becoming 4. You've probably seen the poster image without realizing what you were looking at. A bright little galaxy in the middle, and around it, 4 sharp points of light, like a tiny cosmic diamond or a celestial plus sign. You know the one. That's an Einstein cross. Not 4 separate quasars, but a single background quasar, copied by gravity and arranged around a foreground galaxy. Because here's what nobody tells you. Each of those points is not a duplicate in the sense of a photocopy. It's the same quasar seen along a completely different route through curved space-time. The foreground galaxy is warping the plane of space like a heavy marble on a trampoline, and light can sneak around that marble on multiple sides, fall through deeper gravitational valleys, or skim along shallower ridges. So each image corresponds to its own path, its own length, its own detour through the galaxy's gravity well, its own climb back out. Some paths are shorter in pure distance, but plunge deeper into the potential. Others are longer, but follow gentler curves. General relativity adds both of those ingredients together to decide how long the trip really takes. That means there's a built-in delay between the copies. The quasar flickers, flares, or dims, and you don't see that change in all four images at once. One brightens tonight, another echoes it days later, another, weeks. It's like hearing the same thunderclap bouncing off different canyon walls in space. Astronomers actually sit and watch these flickers. They track the light curves of each image, line up the repeating patterns, and measure the time delays with brutal precision. Those delays aren't just a curiosity. They're equations written in light. They encode the exact geometry of the lens, how mass is distributed in the foreground galaxy, how much dark matter is sitting in the halo, even how clumpy that invisible cloud of gravity really is. And here's the twist that reaches far beyond one lens. The size of those delays also depends on the scale of the entire universe, on how distances stretch as space expands. If you know the lens mass well enough, the time delays become a ruler for a cosmic expansion, a way to infer the Hubble constant without relying on supernovae or the cosmic microwave background. So, if we can already weigh galaxies and test cosmology with these lensed crosses, what happens when we combine them with ultra-precise Einstein rings? Could a sky full of perfectly mapped halos and crosses finally settle the tension over how fast the universe is growing, or will they reveal that the picture itself is still incomplete? Now let's begin to peel back that next layer. By questioning something so basic you almost never think about it. What does it even mean for light to go straight through space? On Earth, your intuition lives inside rooms. Straight walls, flat floors, ceiling above, ground below. You know the one. The mental picture where space is just a gigantic version of that room. An empty, rigid container where things move like billiard balls on an invisible table. Because here's what nobody tells you. That whole picture quietly smuggles in the idea that space itself is flat and passive. Einstein looked at that and said, no, space isn't the stage. Space is in the cast. In general relativity, space-time doesn't just sit there while gravity does the work. Space-time is what gravity is. Mass and energy reshape the geometry, and then that geometry tells everything how to move. Planets, gas, dark matter, even photons that are supposed to be the ultimate straight-line travelers are all just following the local, straightest possible paths laid down by curved space-time. So when you see an Einstein ring, you're not just seeing a pretty halo. You're watching the geometry of the universe autograph itself on a beam of light. A distant galaxy sends out photons in all directions. A massive galaxy or cluster in front of it carves a dimple in space-time. Those photons skim around that dimple along paths that look bent in our diagrams, but in the curved geometry, they're still going straight. The result on the sky? A circle of light that isn't a real object. It's a visible trace of curvature. It's like space-time picked up a pen and signed its name around the lens. And yet, something is above the planets, something is below them. In our solar system diagrams, that above and below are just distances from a chosen plane. With Einstein rings, you're seeing the same kind of choice in disguise. Every flat sketch of a light ray, every tidy orbit, every side view of a galaxy cluster is a projection of a deeper, curved reality onto a flat screen or a flat page. We draw arrows and straight lines because it feels natural. But the ring is a moment when the universe politely taps you on the shoulder and says, "That line you drew, not straight where it really counts." So, let's start at the very beginning of a new habit. When you look at any astronomy picture from now on, ask yourself, straight according to whom? Is that path straight in the diagram or straight in space-time? If space is a co-author, not a backdrop, then you're not just someone who knows facts about gravity. You're someone who instinctively questions the flatness of the picture. And once you do that, the next question almost asks itself. If space can bend light into a ring, what else about empty space have we mistaken for a simple, blank stage? So if space isn't a blank stage, if it's quietly co-authoring the path of light, then there's a question we almost never ask. Right now, in this exact moment, how many Einstein rings are being drawn across the universe that no one will ever see? Not just the famous ones, not just the pretty blue arcs and Hubble posters. We mean every ring, every arc, every tiny smudge where some mass, somewhere, has lined up with some background galaxy or star and bent its light into a halo. Because here's what nobody tells you. Gravitational lensing isn't rare. Alignment is. Wherever there's mass in a background source, there's lensing. A galaxy cluster like Abell 370 turns into a cosmic funhouse mirror, stretching distant galaxies into giant arcs. A single foreground galaxy can sculpt a nearly perfect ring, like the cosmic horseshoe. A lonely star in our own Milky Way can briefly magnify a more distant star into a tiny, perfect circle. You know the one, the classic Einstein ring diagram, the neat circle of light wrapped around a dot. That picture is happening all over the sky, but we don't see most of it. Our telescopes have finite resolution. If the ring is too small on the sky, it just looks like a slightly brighter point. If the source is too faint, the ring is buried in the noise. Micro-Einstein rings from stars, planets, even rogue black holes flicker into existence and vanish again, completely unresolved, like someone drawing circles that are thinner than a single pixel. And yet, something is above the planets. Something is below them. It's this invisible jungle of warped light. The solar system is sitting inside a universe where the entire sky is being very gently twisted, sheared, and magnified by foreground mass. Weak lensing stretches the shapes of distant galaxies by a few percent, so subtly that any one galaxy just looks a little weird. Only when you average millions of them do you see the pattern hiding in the apparent chaos. So how do we even begin to count the unseen rings? This is where the big surveys come in. Projects like the Dark Energy Survey, the Euclid mission, and the Vera Rubin Observatory are built to scan huge swaths of space over and over, hunting for those tiny distortions and sudden micro-lensing brightening events. They're less like telescopes taking pretty pictures and more like forensic cameras, looking for the fingerprints of gravity on the background light. Now, let's begin to imagine what happens as those instruments improve. The sharper our resolution, the deeper our sensitivity, the less flat the sky will look. What you think of as a calm, static picture will start to look restless, crowded, almost tangled with hidden rings and arcs. At some point you have to ask, are we seeing the universe? or just the tiny fraction our current eyes are capable of catching. Because once you accept that the sky is already full of invisible halos, another, stranger question appears on the horizon. And that's where we're going next. So let's pull the emergency brake for a second and ask a question that sounds almost illegal in modern cosmology. What if there were no dark matter at all? No invisible halo? No hidden mass? Just the stars, the gas, the black holes we can actually see bending light in space? Could the universe still look the way it does through the lensing picture we've been building? Could you still get those wild arcs and clusters, those nearly perfect Einstein rings that seem to orbit ghost galaxies? Because here's what nobody tells you when you first see a dramatic Hubble image of a lensing cluster like Able 370. If you take only the visible galaxies in that cluster, add up their stars, their hot gas, their central black holes, and then ask general relativity how much they should bend. Light, you come up short, way short. The predicted rings would be tiny. The multiple images would be weaker and rarer. The sky would not be nearly as tangled with distorted background galaxies as our telescopes actually reveal. In other words, if we insist the universe is built only out of what shines, strong lensing should be a rare party trick. Instead, it's practically a design feature of massive clusters. So you might try to rescue the picture by changing gravity itself. You know the one, modified Newtonian dynamics, and its more sophisticated relativistic cousins that try to fix galaxy rotation curves without adding invisible mass. They tweak how gravity behaves at very low accelerations, and on the scale of a single galaxy's orbit speeds, they can do surprisingly well. But when you throw them at detailed lensing maps of clusters, they start to sweat. Those long blue arcs wrapped around clusters, the way multiple background galaxies get sheared into different shapes at different radii, the way an Einstein Ring's radius pins down the enclosed mass like a ruler pressed against space itself. The numbers just don't line up cleanly without extra matter. That's the quiet superpower of an Einstein Ring. Its size is not a vibe, it's a measurement. For a given geometry, observer, lens, source, the ring radius tells you how much mass has to sit inside that circle, over and over, from the cosmic horseshoe to intricate JWST lenses. The mass implied by the ring exceeds the mass in stars and gas by factors of several. So, let's start at the very beginning of this thought experiment and be honest. Either there is unseen mass, or gravity behaves in a way that just happens to perfectly imitate unseen mass in every lens we measure. And yet something is above the planets. Something is below them. In the same way, something extra seems to sit above and below the visible galaxies in these clusters, shaping light into halos. The debate over dark matter versus modified gravity isn't completely closed, but Einstein rings are some of the most visually persuasive, quantitatively unforgiving clues we have that the universe is holding more than it lets us see. Which raises the next question: if that invisible mass is really there, what is it actually made of? If gravity can hide matter, could it also become our greatest telescope? Not just as a cosmic curiosity, but as an actual piece of hardware in our observing toolkit. Because here's what nobody tells you. We already know how to build a mirror the size of a star. We just have to go far enough away from it. This is the idea of a gravitational telescope. You take a massive object, let its gravity curve space-time, and you sit in exactly the right place so that light from something far behind it gets bent toward you. The object isn't a lens in the glass sense, but the curved geometry around it behaves like one. In principle, that lens can magnify distant galaxies or even tiny exoplanets far beyond what any mirror we bolt onto a rocket could ever do. So let's start at the very beginning of the wild version of this idea, using our own sun. Theory says that if you ride a spacecraft straight outward along almost any line, there's a special region starting at about 550 astronomical units where the sun's gravity brings light from a background target into focus. From that vantage point, light from a distant star or planet would not just look brighter. It would wrap into an Einstein ring around the sun's edge in your field of view. You know the one, the classic ring picture we've been talking about. But this time you're not just admiring it. You're parking your observatory right in the focal line of curved space-time. Futuristic mission concepts suggest putting a spacecraft out there, locking it onto a single exoplanet, and letting the sun act as a lens so powerful you could, in theory, reconstruct continent-scale features. Oceans, ice caps, maybe even seasonal changes in cloud patterns, all from dozens of light years away. How different would "is there life there" feel if you could actually map the weather? Of course, there's a catch. Several, actually. That focal region begins more than 10 times farther than Pluto's orbit. With current propulsion, you're talking many decades of travel just to reach the starting line. Then you have to keep the spacecraft aligned with the sun and the target world as both move in their own orbits. Which means sliding along a line hundreds of astronomical units long while never losing the ring. And the image you get is not a neat little exoplanet portrait. It's a distorted ring-shaped smear of light that encodes the planet's surface in a scrambled way. To turn that into a map, you have to scan, deconvolve, and solve an inverse problem that makes regular telescope image processing look like drawing with crayons. And yet, something is above the planets. Something is below them. In this case, it's curved space-time itself, quietly offering us a lens. If we ever pull this off, we won't just be building a bigger telescope. We'll be engineering with Einstein's equations, treating the geometry of space as an optical element. So what happens when we stop only observing these rings and start using them to read the invisible matter that creates them? Because here's what nobody tells you. If we didn't learn to read these warped halos of light, the universe would still fool us. And we'd never even notice. Imagine a version of astronomy where we just shrug at lensing. You point a telescope at a distant galaxy, you see it looking a little brighter, a little stretched, maybe pulled into a faint arc, and you just write down, "Oh, that one's huge and close." On the sky, it's bigger. So in your notes, it's bigger. Simple. Wrong. Without lensing corrections, our cosmic tape measure breaks. Those magnified galaxies behind clusters like Abel 370 would trick you into thinking star formation was more intense, that early galaxies were fatter, brighter, more evolved than they really were. You'd misjudge how fast galaxies grew, how quickly heavy elements built up, how the whole cosmic web assembled. Your timeline of the universe? Skewed from the first page. And that's just the visible light. The deeper loss is the invisible picture. Because all those arcs and partial Einstein rings are how we map dark matter, the hidden mass that doesn't glow but absolutely controls the architecture of the cosmos. If you ignore the way background galaxies shear and stretch, your map of dark matter is blank. No filaments, no halos, no invisible scaffolding. You'd still see galaxy clusters, sure, but you'd miss the fact that most of their gravity isn't in the glowing galaxies at all. It's in huge, transparent clouds of dark matter wrapping around them. The cosmic horseshoe would just be a pretty ring, not a precise weighing scale for an otherwise invisible galaxy. You know the one, the gorgeous blue loop around a reddish core. Without lensing physics, it's just a screensaver. With it, it's a mass measurement. And yet something is above the planets. Something is below them. In this story, it's not just curved space-time as a lens. It's curved space-time as a clock. Time delays in lensed quasars, where the same flickering quasar appears in multiple spots, each one arriving at a slightly different time. Let us measure how fast space itself is expanding. If we throw that away, one of our cleanest cross-checks on the expansion rate of the universe just vanishes. No extra test of gravity, no second opinion on cosmology. Einstein rings and arcs are not just pretty pictures for press releases. They are dense with data. The radius of a ring tells you the mass of the lens. The thickness and sharpness tell you about how that mass is distributed. The color and distortion of the background galaxy reveal what galaxies looked like billions of years ago, when the solar system was still a future possibility in some collapsing cloud. So when you scroll past an image from Hubble or JWST and see a delicate blue arc curving around a golden galaxy, you're looking at a secret layer of reality. If you don't know lensing, it's just an aesthetic curve. Once you do, it's a message. Here is hidden mass. Here is bent time. Here is a magnified shard of the early universe. Now let's begin to really decode that message, because the next trick lensing plays on us is even stranger than a simple ring. Now let's begin with a slightly uncomfortable truth. Those gorgeous Einstein Ring images you've seen? They are the tiniest fraction of what's really out there. Our telescopes are pulling down so much sky that if we tried to scroll through every galaxy by hand, you'd be here until the heat death of the universe. Because here's what nobody tells you. Modern sky surveys don't give us a neat little scrapbook of pretty galaxies. They give us databases, oceans, the Sloan Digital Sky Survey, the Dark Energy Survey, Euclid, the Vera Rubin Observatory. Together, they're capturing billions of galaxies. Hidden in that flood are the rare ones where gravity has drawn a ring, or an arc, or a horseshoe of light. But those rings might appear in tens of thousands of galaxies. You will not find them by casual stargazing. So how do we hunt for halos of bent light in this blizzard of data? We teach computers what a ring looks like. You know the one, a central bright blob with a faint blue arc wrapped around it, like the cosmic horseshoe, or those eerie blue rings around massive elliptical galaxies in Hubble images. Astronomers feed machine learning algorithms thousands of examples of confirmed lenses and thousands of normal galaxies. The code learns subtle patterns in shape, color, and symmetry that your eyes notice but can't easily describe. Then we unleash it. The classifier races through millions of images, flagging anything with ring-like or arc-like features. Most of what it finds is junk. Spiral arms, overlapping galaxies, weird instrumental ghosts. But sprinkled through the false alarms are genuine candidates, places where gravity might be quietly turning the universe into a hall of mirrors. And yet something is above the planets. Something is below them. In the same way, something is above and below those algorithms too. Ordinary humans. Before the machines got good, projects like Galaxy Zoo invited volunteers to click through real survey images and tag anything unusual. Among the mergers and ring galaxies and plain old ellipticals, people started spotting possible gravitational lenses. Those human-labeled oddities became training data, sharpening the automated searches. It's a feedback loop. The crowd teaches the machine finds more candidates. The experts confirm the best of them. Confirmation is where the real detective work begins. We point sharper eyes, Hubble, JWST, big ground-based telescopes with adaptive optics, at the candidates. If the ring sharpens into multiple mirrored images, that's a strong hint. Then spectroscopy measures redshifts, the central lens galaxy at one distance, the ring at a completely different one, same line of sight, different layers of the universe. That's the smoking gun for lensing. So what happens when AI gets even better? Suddenly Einstein rings stop being rare curiosities and become a population. Tens of thousands, maybe hundreds of thousands, each one tracing the invisible gravity field of dark matter, each one a precise ruler for cosmology. And we're only just starting to see how that changes the picture. But those are the tame cases. Galaxies, clusters, big smooth halos of dark matter. Once you can find tens of thousands of those, you start to wonder, what happens when lensing gets weird? When the universe throws us something that doesn't fit the usual picture of a nice, round mass, bending light into a nice, round ring. Because here's what nobody tells you. The same equations that describe a graceful Einstein ring around a galaxy will also describe light skimming the edge of a black hole. If you could line up a distant star, a solitary black hole, and Earth almost perfectly, gravity would whip that starlight around into a tiny, blazing ring. A black hole halo of light. In principle, it's the cleanest Einstein ring you could ever see. In practice, that alignment is absurdly rare. The angular size is microscopic, and the whole event could be over in days or weeks as the orbits shift. We hunt for hints of those with microlensing surveys that stare at dense star fields, watching for little blips in brightness. As compact objects drift across our line of sight, most blips come from ordinary stars. But hidden in that sea of flickers, we could catch a black hole lens, a light curve that brightens and fades with no light from the lens itself, just pure gravity, announcing that something dark is there. Now let's begin to really push it. Imagine an object we've never directly seen, a cosmic string. You know the one, the hypothetical crack in space-time itself, stretched across the universe like a fault line. A string doesn't curve space into a bowl, it cuts a wedge out of it. So instead of a ring, you'd get double images of the same galaxy, neatly duplicated and slid apart, with a sharp, line-like distortion between them. No fuzz, no arc, just a cosmic photocopier error running straight across the sky. So, let's start at the very beginnings of time and get even stranger. If primordial black holes formed in the first fractions of a second after the Big Bang, they could be drifting through space today as part of the dark matter. Each one would have a minuscule Einstein radius, far smaller than a galaxy's, but microlensing could still betray them. A background star would brighten in a very specific, symmetric way as the tiny lens crossed the line of sight. No atmosphere, no solar system, no glare, just a bare point mass-bending light. And yet something is above the planets. Something is below them. Out in intergalactic space, beyond our neat diagrams and flat planes, these exotic lenses would obey the same math as the pretty rings we've already seen. Most of the Einstein rings we know come from galaxies and clusters, but the door is open. If we ever catch a ring that's too sharp, too thin, or split in some impossible pattern, what will it be telling us? That dark matter is made of unexpected objects? That gravity itself changes on certain scales? Or that there are entirely new kinds of mass hiding in the cosmic cloud, waiting for their light-bent signatures to cross our orbit and force us to redraw the picture yet again. So here's the uncomfortable truth hiding inside all those beautiful rings and arcs we've been talking about. Your brain was not built for this. Light wrapping around galaxies in a four-dimensional curved space-time. You're a primate that evolved to throw rocks and not walk into trees. Of course, your intuition rebels, because here's what nobody tells you. Your visual system comes with a hardwired geometry pack. It assumes the world is Euclidean. Straight lines stay straight, parallel lines never meet, and flat surfaces extend forever without surprise. That works brilliantly for a village, a city, even for the way we picture the solar system as a neat, clockwork disk. But on cosmic scales, those assumptions quietly fail. When gravity gets strong enough, the straightest possible path for light is no longer what your eyes think a straight line should look like. In general relativity, light follows geodesics through curved space-time, not the ruler straight rays you drew in school. So, when you see an Einstein ring, you're not seeing a special effect layered onto a flat background. You're seeing what straight actually means near a massive object. That's why these rings are so powerful for your intuition. They're training wheels. Instead of asking you to imagine all of space-time bending in some abstract four-dimensional way, they give you one very specific pattern to hold on to. A circle of light around a mass when the source, lens, and observer line up. You know the one. It looks like a glowing halo, a perfect space donut that your Euclidean brain can at least recognize as a circle. So, let's start at the very beginning of how we cope with this. We cheat. We use multiple mental models, and we switch between them depending on what feels clearest in the moment. Sometimes we roll out the trampoline analogy. A heavy ball sagging the fabric, marbles curving around the dent. Other times we go to the airplane on a globe analogy. The shortest route isn't the straight line on the flat map, it's the great circle on the curved Earth. And then there's the precise source lens observer diagram. No trampoline, no globe, just you, a foreground galaxy and a background galaxy all lined up in space. Rays leave the distant galaxy, curve around the lens, and still reach your telescope, forming that ring. Each picture lies to you in a slightly different way, but together, they start to triangulate a new kind of intuition. The key move is noticing the moment your gut says, that can't be right. When parallel light rays meet, when one galaxy becomes four images, when a ring appears where no object actually sits. If you can catch that flicker of discomfort and not shut down, you've just found the edge of your everyday experience. That edge is where learning actually happens. Because once you get comfortable feeling lost in curved space-time for a second, you're ready for the next leap. What happens when the lens itself is moving, changing, or not even made of normal matter at all? Here's where the whole picture flips. Up to now, you've been trained on diagrams where gravity is drawn as little arrows and light is drawn as straight lines. Neat, clean, flat. In that picture, space is just an empty stage, and gravity is this invisible hand tugging planets and apples, and you toward massive objects. You know the one. The classic textbook scene. A sun in the middle, planets on circular tracks, maybe some blue arrows pointing down toward the surface of Earth. And if a beam of light bends, in that old story, it's because it hit glass, or a mirror, or some lens in a telescope. Otherwise, light minds its own business and goes straight. Because here's what nobody tells you. That whole flat arrow picture is a shortcut, not reality. In Einstein's version, there is no extra force reaching out across empty space. mass and energy reshape the arena itself. They curve space-time and then everything, planets, comets, photons from a distant galaxy, just follows the straightest possible paths inside that curved geometry. Those paths are called geodesics. Locally, to the light, they feel perfectly straight. No drama, no sideways yank. But when we project those paths back onto our old flat mental screen, they look bent, twisted, even looped into circles. The weirdness isn't in the light, it's in the way we were drawing the stage. So, let's start at the very beginning of this new picture. Stop thinking of gravity as arrows, and start thinking of it as invisible scaffolding. A warped, flexible grid that tells matter and light how to move. Put a galaxy cluster on that grid and it sinks in, like a heavy bowling ball on a trampoline. Now fire a beam of light past it. On the trampoline, the straightest line curves around the dent. From far away, that curved straight line is what we call gravitational lensing. And when the alignment is just right, background galaxy, massive lens, and you all stacked almost perfectly, you don't get a random squiggle. You get a ring, a clean circular halo of light where no actual object sits. That's an Einstein ring. It's the emblem of this entire shift, the place where the old Newtonian picture just runs out of explanations. There's no way for gravity as a pulling force in a flat space to neatly wrap light into a perfect circle around an invisible center. But in general relativity, it just drops out of the math like it was always supposed to be there. And yet something is above the planets. Something is below them, not in the sense of a cosmic floor or ceiling, but in the sense of extra directions in this curved scaffolding that our flat sketches never show. Under the right conditions, that hidden depth can twist light into arcs, doubles, even full halos. Pattern interrupt. The next time you see a flat gravity diagram, mentally peel it up into 3D. Ask yourself, if I could see the curvature that picture is hiding, where would the light go? Could that simple little arrow diagram secretly contain a ring? Because once you start seeing gravity as living geometry instead of invisible pulls, Einstein rings stop being space donuts and become something stranger, a direct photograph of space-time itself. Now let's begin to push this even further. What if that curved scaffolding is changing while the light is already on its way? If that scaffolding can change while the light is already on its way, here's the next twist. What direction is that change even happening in? Up, down, sideways. In space, there is no up, there is no down. There is only relative to what you decided to call zero in the first place. Because here's what nobody tells you. When you look at an Einstein ring, your brain secretly imports the same habits it learned from the flat solar system picture. You know the one, a nice horizontal plane, planets above and below, gravity pulling down into a bowl. But out there, around a distant galaxy acting as a lens, there is no cosmic whiteboard with a top edge and a bottom edge. The ring itself doesn't have a top or a bottom. It's perfectly symmetric around your line of sight. Rotate the telescope image by 90 degrees and nothing physical has changed. Tilt your head the other way and suddenly a point that felt above the lens galaxy is now to the left. Which one is right? All of them and none of them, because the ring only cares about angles from your viewpoint, not about some hidden universal vertical. Astronomers know this, so we cheat in a very honest way. We choose coordinates. On the sky, we use right ascension and declination, the celestial version of longitude and latitude. On an image, we talk about X and Y pixels. Those axes feel solid, but they're conventions, not commandments from nature. Turn the camera and the same Einstein ring that used to be stretched up and down. The frame is now stretched left and right. The geometry is identical. The labels are all that moved. And yet something is above the planets. Something is below them. In the solar system, we smuggle in that language by anchoring everything to the ecliptic plane. With lenses, we do the same trick with whatever grid the observatory software draws on the screen. It's useful. It lets you say, the bright arc is 3 arc-seconds north of the lens galaxy. But that north is just bookkeeping, not a real direction carved into space-time. This is where our diagrams quietly mislead us. That classic rubber sheet picture with a heavy mass sinking into a funnel and light falling around it almost dares you to imagine a literal downwards pull. In reality, light in an Einstein ring is following geodesics, straightest possible paths in a curved, direction-neutral space-time. There is no bowl. There is only geometry. So when you see that halo of light, don't picture photons sliding into a cosmic drain. Picture a 3-dimensional web of paths, all equally valid, all wrapped around a mass. The ring is just where those paths happen to intersect your eye. Which raises a bigger question. What happens when the lens itself is moving through that web while the light is still en route? It means the sky is not a still photograph. It's a hall of mirrors that's moving. Because once the lens starts drifting through that web of paths, the apparent positions of those background galaxies can jump, split, and smear. Strong lensing turns one quiet galaxy into a whole cast of characters. You get a stretched arc over here, a tiny duplicate over there, sometimes a full ring wrapped around a foreground mass like a glowing cosmic bracelet. Same galaxy, different mirrors. You know the one, the classic funhouse mirror that makes you tall in one panel and squashed in the next. Strong lensing does that on the sky. It takes a single, distant source and lets gravity carve it into multiple images, each one a distorted reflection of the same underlying reality. The universe looks smooth and flat to your eye, but hidden in that picture is a jagged landscape of space-time, quietly warping the view. Because here's what nobody tells you. In some regions of the sky, you can point your telescope at 2 patches separated by arc minutes and be looking at the same galaxy twice. The light left that galaxy along different routes, skirted around different sides of a cluster, and arrived at your detector at slightly different times. To you, they're just 2 faint smudges. To general relativity, they're parallel stories of the same event. Push this idea far enough and it gets wild. In principle, light could loop around massive structures multiple times before finally escaping toward us, tracing closed paths that wind through the same gravitational maze again and again. A photon could orbit a black hole, peel off, swing past a cluster, and only then wander into your telescope. Those extreme loops are rare in practice, but the possibility is baked into the geometry. Space doesn't promise you a straight line. It promises you whatever path the curvature demands. So what are we really seeing when we look out? Not the universe as it is, but the universe as filtered through space-time, through our instruments, through the coordinate grids we choose to draw on top of it. There's always mediation. There's always a lens, whether it's a galaxy cluster or the glass on your camera or the math in your head. The true arrangement of matter and light is something we infer, never something we simply witness. And that's why Einstein rings are so honest. They don't pretend to be a clean window. They show that they're a projection. When a background galaxy becomes a perfect circle, the sky is basically confessing, this is not where that galaxy is, in any simple sense. This is the footprint of curved space-time on your retina. Now let's begin to ask a more unsettling question. If gravity can redraw the map of where things appear, what else can it do to our sense of when things happen? So here's the twist. Long before anyone could actually see a halo of light around a galaxy, Einstein had already drawn it with equations. He's sitting there in the early 1900s, turning this wild idea over in his head. Gravity isn't a force pulling on you. It's the geometry of space-time telling you how to move. If that's true for planets in orbit, it should be true for light in space as well. So he runs the math. Light should bend around the sun. Not just a little, by a very specific angle. Because here's what nobody tells you. Those rings and arcs you see in Hubble and GRWST images are not just pretty. They're graded homework. In 1919, during a solar eclipse, astronomers measured starlight bending around the sun and got almost exactly the value general relativity predicted. Decades later, the same equation said, in principle, you could get a complete circle of light if a source, a lens, and an observer lined up perfectly. You know the one, the space donut you've seen in press releases. That ring has a size, an angular radius on the sky, called the Einstein radius. And that radius is fussy. Change the details of gravity, and it changes too. In general relativity, the bend and angle depends on the mass, the distances, and the exact way space-time curves. Alternative theories of gravity often sneak in different distance dependencies, or extra fields, or tweaks to how fast gravity propagates. On paper, those tweaks mean different ring sizes, different arc shapes, different brightness patterns. So when we measure an Einstein ring around a galaxy like the cosmic horseshoe, we're not just weighing the galaxy. We're asking, does this match the curvature that Einstein's equations demand? So far, across hundreds of strong lenses on galactic and cluster scales, the answer is yes. Within the fuzz of our measurement uncertainties, the arcs behind clusters like Abel 370, the nearly perfect circles, the multiple images that pop up like mirror reflections in space, all sit right where general relativity says they should. Pattern interrupt. That doesn't mean we're done. Far from it. Researchers are now zooming in, pixel by pixel, hunting for tiny mismatches. Is one image a hair too bright? Is a ring slightly thicker on one side than pure relativity plus dark matter would allow? Could that be a hint of quantum gravity, or a new field threading through the cosmos, or a subtle failure of Einstein's picture in the deep universe? And yet something is above the planets. Something is below them. Every time we see a clean Einstein ring, we're looking at a photograph of geometry itself, a frozen imprint of curved space-time, a century-old idea, scribbled as symbols on paper, still drawing perfect circles of light on the sky. The next question is, if the geometry holds this well in space, what happens when we push it in time? So if curved space-time can draw such perfect circles of light out there, the obvious question is, could you ever just walk outside, look up and see it happen with your own eyes? No telescope, no long exposure, just you, the night sky and gravity quietly bending to the picture. Because here's what nobody tells you. Almost all the dramatic lensing you see in posters and press releases is happening with objects that are both incredibly distant and incredibly faint. Those giant arcs wrapped around galaxy clusters. Some of them span angles larger than the moon in the sky. If your eyes were sensitive enough, You could trace those warped crescents without any help. But we're not built like a space telescope. The light is too dim. The details are smeared out by our own biology. So let's start at the very beginning of the question. What lenses are close enough and bright enough that we might have a shot? You know the one. The sun is the biggest mass we have easy access to. It absolutely bends light. During a total solar eclipse, background stars appear shifted outward by about 1.75 arc seconds at the sun's edge. That angle is tiny. Your eye's resolution on a dark, steady night is maybe 60 arc seconds or so. The deflection is over 30 times smaller than what you can perceive. To you, the stars look perfectly normal. Only a camera and careful measurement reveal that their orbits on the sky have been nudged. Planets do it too. Jupiter, with all its bulk, can lens background stars by milliarcseconds. That's 1,000th of an arcsecond. From the ground with your eyes, that's not just subtle, it's invisible. Even if we arranged a perfect alignment of Earth, Jupiter, and some bright star, you wouldn't see a ring, or an arc, or even a wobble. The geometry is real. The effect lives below your built-in pixel size. So we cheat. We stack images, we stretch contrast, we let Hubble and JWST stare for hours. We turn the universe into long exposure art, just to coax these halos of light out of the noise. And yet something is above the planets. Something is below them. A whole invisible scaffolding of bent paths that your brain insists are straight. Could there be a scenario where you really would see the sky warp in real time? In principle, yes. Imagine a supermassive black hole, millions of solar masses, passing through the outer reaches of the solar system. Far enough not to shred Earth. Close enough that its Einstein ring on the sky might be a degree wide. In that nightmare-adjacent thought experiment, the constellations around it would twist, double, and smear into arcs you could point at with your finger. No telescope, just raw, terrifying geometry. But events like that are fantastically unlikely on human timescales. The universe is big, the dangerous masses are rare, and our little orbit is mostly quiet. So we live in a world where space-time is always bending light, yet almost never dramatically enough for you to notice. That's the deeper point. Our senses are tuned to straight lines in a very gently curved universe. To see the true shape, we have to build extensions of ourselves, glass, silicon, and software that can pick out microlensing blips and stretched galaxies. Once you realize how much work it takes just to see one ring, you start to wonder, how many more lenses are there that we never notice, simply because they only flicker for a moment in time? So let's pull back for a second. We started this whole journey with the simplest picture you could draw on a napkin. Straight light rays as tidy arrows, gravity as a downward pull, and empty space as a blank, flat stage where all the action happens. You know the one. Light goes in straight lines. Planets orbit in neat ellipses, and the universe behaves itself. Because here's what nobody tells you. That picture is training wheels. It works for short distances and weak gravity. But the moment you ask why starlight bends near the sun, or why a galaxy can look like a smear in a Hubble image, the flat diagram collapses. We had to upgrade from space as a backdrop to space-time as an actor. Mass doesn't just sit in space. It tells space and time how to curve, and that curvature tells light which way to go. So, let's start at the very beginning of that upgrade. We traded in straight Euclidean lines for geodesics, the straightest possible path in a warped geometry. We watched how stars behind the sun appear shifted during an eclipse. not because the stars moved, but because their light followed curved tracks through the sun's gravitational field. Then we scaled up. One star became a galaxy. One sun became a whole cluster. Suddenly, the same rule that nudges a ray by a fraction of a degree can shear a galaxy into an arc. And that's the key step. Light doesn't go straight in our naive sense. It goes straight in space-time sense. When the geometry is warped just right, those geodesics wrap light into multiple images, long stretched arcs, or, on those rare, exquisite alignments, a full Einstein ring. A distant galaxy, a massive lensing galaxy in front of it, and you lined up along almost a single line. That's all it takes for gravity to sketch a halo. But look at a Hubble or JWST image of a ring, and your brain rebels. It looks like a solid object, a literal glowing hoop in space. And yet, something is above the planets. Something is below them. In the same way, what seems like a physical ring is actually light from one remote galaxy, rerouted along many paths by an invisible mass distribution we can only infer. The ring is a map of gravity, traced in photons. Now we need a final mental model that can hold both truths at once. On one level, keep the simple picture. Background source, lens, observer, like beads on a line. On the deeper level, see space-time itself as the medium, doing the bending, the way a glass lens bends rays in your eye. Because once you can switch between those two views on demand, something wild happens. You start to realize that every space donut we photograph is also an X-ray of the dark universe. And in the next part, we're going to read those X-rays for what they really say. So now we turn that wild idea into a tool, a habit, your new X-ray vision for space images. Because here's what nobody tells you. Once you see an Einstein ring properly, you can't go back to just a pretty picture of a galaxy cluster. You start reading mass. You start reading gravity. You start reading the hidden architecture of the universe from a single glowing halo. So, let's start at the very beginning of that process. Next time an image flashes by on your feed, some JWST deep field, some Hubble cluster with a poetic name, don't just zoom in on the brightest galaxy. First, pause. Ask yourself, where's the lens? Look for the chunky central galaxy, or the dense knot of galaxies that everything seems to orbit visually. That's your foreground mass, the thing actually doing the bending. Then do something slightly weird. Imagine a second galaxy that you can't see at first, sitting directly behind that lens along your line of sight. Picture it much farther away, like a lighthouse hidden behind a city skyline. That's the background source. In a perfect alignment, you, the lens, and that distant galaxy all lie on almost the same straight line in space. Now trace the light. In your head, turn that background galaxy into a fire hose of photons, spraying out in all directions. Some head off into deep space and never meet us. But some skim past the lens galaxy, just close enough that its gravity curves their path inward. They don't crash into it, they slingshot. They bend through warped space-time, then keep flying until, much later, they hit the tiny circle we call Earth. From our point of view, those bent paths line up around the lens. They arrive looking like a ring, or an arc, or multiple stretched smears wrapped around the central galaxy. You know the one. The cosmic horseshoe, the delicate blue arcs in clusters like Abel 370, the absurd space donuts in recent JWST images. And here's the upgrade most people miss. The size of that ring is not just an aesthetic choice by the universe. It encodes mass. A bigger Einstein ring means the lens is packing more gravity inside that radius, not just visible stars and gas. but a huge cloud of dark matter that you cannot see in any other way. The ring is literally outlining the invisible. So try this experiment. The next time a telescope image goes viral, stop and ask, is there any sign of lensing here? Any arcs that look too smooth, too circular, to be random? If yes, you're not just looking at galaxies. You're watching the geometry of space-time flex under weight. From now on, you're not just scrolling past flat pictures. You're reading the fingerprints of gravity, written in halos of light. And yet, something is above the planets. Something is below them. In the next part, we'll push that idea out to full cosmic scale and see what those fingerprints reveal about the dark universe itself. So let's come back to that first impossible picture we started with. You're staring at a glowing halo wrapped around a galaxy, a perfect ring. It looks like the galaxy has grown a luminous crown. But the halo isn't really there. The light belongs to a completely different galaxy, far behind it, dragged into a circle by gravity and lined up just so along our line of sight. Because here's what nobody tells you. The sky you see is not a simple address book of where things are. It's a projection. It's a warped, curved, time-soaked image painted onto a dome above your head. When you look at an Einstein ring, you're not seeing a thing in space. You're seeing the path light was forced to take through space-time before it finally hit your eyes. In a flat textbook picture, that sounds abstract, but once you've watched a background galaxy twisted into a horseshoe, or a nearly perfect circle like the cosmic horseshoe or the jackpot Einstein ring, it lands differently. You realize the universe isn't just placing objects on a three-dimensional grid. It's bending the grid itself, then letting light trace out the dents. So what does that do to your sense of reality? If a single galaxy can wear the face of another like a mask, if a tiny misalignment can turn one distant source into 4 separate images, how confident are you that there on the sky really means there in space? In a way, we're all using a funhouse mirror as a map and calling it a flat photograph. And Einstein rings are only one flavor of this. The same geometry gives us the dark, crisp shadow of a black hole where light orbits and almost escapes before giving up. The same equations describe gravitational waves, those ripples in the space-time fabric that make entire galaxies subtly stretch and squeeze as they pass. The same bending of light plays out near neutron stars, where a single compact object can lens its own surface into view. So, let's start at the very beginning of the next question. If gravity can sculpt halos of light out of distant galaxies, what other patterns are hiding in our data? Are there lensing signatures from rogue planets drifting between the stars? Are there delicate rings so small that, right now, they're just one blurred pixel in a survey image? The next time you see a circular halo in a telescope picture, pause. Remember that you're not just looking at a pretty ring. You're watching the universe reveal its own curvature in plain sight. And yet something is above the planets. Something is below them. In the next part, we'll follow those hidden curves out into the dark and see what else the bending of light is quietly trying to tell us. So now that you've seen how gravity can sketch a perfect circle out of a straight beam of light, this is where it becomes your experiment. Your turn to bend light, at least with your eyes. When you look back at those Hubble or JWST images, what hits you first? Is it the impossible symmetry of a full Einstein ring, or the way a single galaxy can be shredded into 4 separate mirages around a cluster? Because here's what nobody tells you. Once you've seen the trick, you can't unsee it. So scroll down and tell us which part of Einstein Rings surprised you the most. Was it that those delicate blue arcs in Abel 370 are really background galaxies being stretched around invisible dark matter? Or that a space donut, like the cosmic horseshoe, is just one galaxy photobombing another along our line of sight? If you've got a favorite ring image, drop it in the comments so we can all orbit around the same picture for a minute. You know, the one friend who loves space wallpapers, who has a galaxy cluster as their phone background, but has never really thought about what those weird curved streaks actually are. This is their episode. If you send them this video, you're not just sharing a pretty compilation of cosmic lenses, you're handing them a new way to read every deep field image they see from now on. It's a small social experiment. Can one explanation of curved space-time quietly upgrade someone's whole mental model of the universe? Now let's begin your next rabbit hole. If the idea that gravity can make a halo of light around a galaxy clicked for you, wait until you see what it does, right at the edge of a black hole. We've got a deep dive on black hole shadows, where light doesn't just bend into rings, it orbits the hole before escaping. From there, you can follow those same principles into dark matter mapping, where weak lensing turns random galaxy shapes into a contour map of invisible mass, and even out into the cosmic web, where the large-scale structure of space itself leaves fingerprints on how distant galaxies appear. If you want more of these deep dives that start with a familiar picture and then flip it inside out, subscribing and turning on notifications genuinely helps us keep making them. Think of it as joining a small observing team. We point the telescope. You bring the curiosity. Thank you for spending part of your day thinking about the shape of space-time, about how a simple ring of light can reveal an entire hidden architecture around a galaxy. And yet, something is above the planets. Something is below them, out there, beyond the solar system's flat diagrams and neat planes. The universe is full of optical illusions we haven't decoded together yet. In the next chapters, we'll keep chasing those bends in light and see what other invisible structures are quietly waiting to be seen. So let's zoom out one more time and ask a question that sounds simple but isn't. How many Einstein rings happen during a human lifetime? Not how many we discover, how many actually form, shift, and vanish in the sky while you're just living your life? Because here's what nobody tells you. The universe only feels frozen because we're tiny. On the scale of galaxies and clusters, everything is in motion. Massive galaxies orbit through clusters. Clusters fall toward each other. Background galaxies drift across the sky. And all the while, light is threading its way through this moving maze. Every strong lens, every halo and arc, is a configuration that's slowly evolving as gravity rearranges the cosmic furniture. So the Einstein rings we admire in Hubble and JWST images are snapshots. You know the one. A bright blue circle wrapped around a golden galaxy. The perfect space donut poster. A few billion years ago, that exact alignment didn't exist. The background galaxy was in a different apparent position. The lensing galaxy's mass was distributed differently, and the light we're now catching hadn't even started its journey toward us yet. Flip the arrow of time the other way. Out beyond our current horizon, light is leaving distant galaxies. Right now, passing behind foreground clusters in just the right way to make new rings and arcs that we won't see for millions or billions of years. Somewhere, a future astronomer will point a telescope at a patch of sky we think we know, and the picture will be different because the universe has had time to redraw the lensing. On human timescales, though, the big dramatic systems are almost statues. Over 80 or 90 years, the strong lenses we catalog today won't twist into some obviously new pattern to your eye. Their orbits through space are slow. Their mass distributions change, but not on the scale of a school year, or a career, or even a single civilization. But down in the small print of the cosmos, things are happening fast. Micro-lensing events, where a single star or planet in our own galaxy briefly lenses a background star, can flare and fade over days, weeks, months. A tiny, perfect Einstein ring forms at the peak of the event. Too small to resolve, but big enough to boost the light. Quasar lens systems can send us multiple flickering copies of the same outburst, staggered by days or weeks of time delay as light takes slightly different paths through curved space. So while you're watching this, there is, somewhere in the sky, a new micro-lensing event just beginning. A star drifts in front of another star, a planet adds its own little tug, and for a short while, there's a perfect invisible halo of light around a point you'll never notice. It forms. It fades. No applause. No audience required. And yet something is above the planets. Something is below them. Above and below are flat solar system diagrams, out in the real three-dimensional universe. Gravity is constantly bending light into rings and arcs whether or not we're paying attention. Our job is to catch a few of those moments, understand what they're telling us about mass and space-time, and let that realization shrink our egos a little. Now let's begin the strangest part. If gravity can redraw the sky, what does that do to our idea of where anything really is? It does something ruthless to our intuition. It means that every straight line you've ever seen in a space diagram is, at best, a polite lie. Because here's what nobody tells you. In a curved universe, straight lines lie, especially when it comes to light. What looks like a clean arrow from a distant galaxy to your eye is actually a path wrapped around invisible wells of gravity, stitched together by space-time itself. Einstein rings are the proof written directly onto the sky. They're not props from a sci-fi movie, not some special effects halo that artists added to make a galaxy look cooler. They're real, observable consequences of mass telling space-time how to curve and light how to move, the way a heavy planet tells the orbits in our solar system where to go. You know the one. The textbook picture with straight rays leaving a distant galaxy, crossing the cosmos like laser beams, and landing in a telescope. Helpful, clean, wrong in all the important ways, because when a massive galaxy cluster sits in the way, those rays bend, split, and wrap into arcs and full rings that Hubble and JWST actually photograph. So here's the mindset shift we want you to walk away with. Anytime you see a straight arrow in a space picture, you should at least wonder what hidden curvature that arrow is ignoring. What dark matter cloud it glided past. What galaxy it skimmed. What black hole it looped around so gently you never noticed. In your head, start replacing those straight arrows with geodesics, with the true, straightest possible paths through curved space-time. That's all an Einstein ring is. Light obeying the rules of geometry in a universe where the grid itself is warped. Once you see it that way, those delicate blue arcs around a cluster stop being pretty decorations and start feeling like confession lines where the universe admits where its mass really is. And yet something is above the planets. Something is below them, not in the old sense of up and down, but in the sense that beyond the flat plane of orbits you learned about, there's a deeper shape to reality that light is quietly tracing for us. Now let's begin the next part of your own orbit through this picture. If you want to keep bending your understanding, following gravity from Einstein rings to black holes to the edges of the observable universe. Hit subscribe. Dive into our playlist on gravity, black holes, and cosmology, and let this channel be your curved path through a very non-flat cosmos. As we fade out, hold one last image. An Einstein ring, bright and sharp, slowly dissolving into a simple curved grid. The halo melts into lines. The lines sink into a warped plane, and you're left with a quiet echo. Space is not what it looks like at first glance. Neither are straight lines.